We're now looking at the substitution method. The substitution method is a method that we can use to help us find the antiderivative or integrate something that we wouldn't be able to integrate otherwise. And so when we're looking to use the substitution method, your integral is going to be in some form where we have a composition of a function, and that inside of the composition of the function, the g of x, you'll notice that there's part of the derivative as that integrand. And so that's what we're trying to figure out what u is going to be. So if u equals g of x is a differential function whose range is an interval I, and f is continuous on I, then the integral of f of g of x times g prime of x dx is the same thing as the integral of f of u du. Okay, so let's look at an example and go through some of these. So let's look at the integral. So a lot of, at the beginning of your homework, they actually give you some of these, but they actually tell you what to use for u. Normally, I wouldn't tell you what to use for u. I would ask you to figure out what u is. But the first couple questions in the homework are a lot easier because they give you what u is. I'm not going to do that though. So let's say that we have the following. We have the integral of 2x all times the integral of x squared plus 5. And this is raised to the 4th power dx. Well, we want to figure out what we want to choose u to be. And whatever we choose u to be, when we take the derivative, we want to see part of that derivative in our function. And so notice this inner piece right here, this x squared plus 5. So let u equal x squared plus 5. If we take the derivative of this piece, so if we take the derivative of u, that's 1 du equals the derivative of x squared plus 5, which is 2x dx. So this is similar to what we were doing in chapter 4, that differentials. And that's where this is important. We want to rewrite our integral, our integrand, to be just a function of u. And notice that we had let u be this piece right here, this x squared plus 5. So if I start to rewrite this, I have the integral of 2x parentheses of u and my parentheses to the 4th power dx. But I want this to be du. So what you're going to do is you're going to go back to where we took the derivative of u equals x squared plus 5 and solve for dx. So over here, we're going to solve for dx. So we can do that by dividing both sides by 2x. If we divide both sides by 2x, we get dx is equal to du over 2x. So instead of writing dx, we're going to rewrite it as du over 2x. If you chose the correct thing for your u, then this should cancel out. There are a couple cases where it doesn't, but I'll show you that where we can manipulate it so it works out. So notice this 2x cancels. And we're left here with the integral of u to the 4th du. Now it's in the form that we know how to integrate this. So integrating u to the 4th, we're adding 1 to our exponent, dividing by our new exponent. This is an indefinite integral, so we don't have bounds. This is where we had to add our constant c. And now that we know what u is, we had used that at the beginning of the problem. We let u be x plus 5. So once we're able to integrate, and once you integrate, then go back and let's replace u with x squared plus 5. So we now have parentheses u, which is x squared plus 5, all raised to the 5th power over 5 plus c. So if we integrated this, so let's say f of x was this, a capital F of x. If we differentiate this, we should get back our integrand, which was this two x all times x squared plus 5 raised to the 4th. So let's just check the derivative of this. Well, we need to use our chain rule. So bring our power down front. So 5 of the inside, x squared plus 5, subtract 1 from our power, it's now 4. That's all over 5, times the derivative of the inside. And the derivative of our inside is 2x. Plus the derivative of c, but the derivative of a constant is 0. So notice here that the 5's cancel. And we have the integrand, which is 2x all times x squared plus 5 to the 4th. And so we did this correctly. Okay, so we're going to just do a lot of these problems. But let me just kind of outline the steps of what we just did and what you're going to be doing when you're going through using substitution for an indefinite integral. I have it somewhere in here. Okay. So here's your guidelines. So given some integral, I equals the integral of f of g of x times g prime of x dx, with f continuous and g differentiable. The following steps outline the substitution rule process for the integrating I. So first thing you're going to do is let u be g of x, that inner function, which is typically the inside function of the function composition in the integrand. Okay. So once we figure out what we're going to choose u to be, you're going to compute du equals g prime of x dx. So you're going to take the derivative of both sides of our equation. Once we've done that, we're going to write our integral I solely in terms of u using either method. So we're going to go back in and we're going to substitute u equals g of x, du equals g prime of x dx, or replace d of x with du over g prime of x and cancel g prime of x. So once you've rewritten your integrand just in terms of u, x is no longer in there, then we can integrate with respect to u. Once we've integrated with respect to u, we can go back in and we can replace u with g of x to rewrite the resulting function in terms of x only. Okay, so it just really is a lot of it is just practice. Also, you're choosing something for you that when we go back and plug it in, we know how to take the derivative of. Or not the derivative, the antiderivative. Okay, so we're looking at the integral of the square root of 3 minus 2x dx. So notice that we don't know how to integrate that. But if we choose u to be what's underneath that radical, we know how to take the square root of x or the square root of u. So let u be that 3 minus 2x. So let's differentiate both sides of our equation. So derivative of u is du equals the derivative of 3 minus 2x is negative 2 dx. And then we want to solve for dx. So we can solve for dx, divide both sides by negative 2. We get dx equals du divided by negative 2. So let's go back in there. Let's replace what dx is. And let's replace what we chose u to be. So we really have the integral now of the square root of u du. Oops, no, we don't. The square root of u du over negative 2. So we can use rules of integration. We can pull, that's really like negative 1/2 times the square root of u du. So we can pull that negative 1/2 outside of the integral if we want. And it helps us if we rewrite u square root of u as u to the 1/2 power du. So now we have the form where we know how to take the antiderivative of the integrand. So let's bring down the negative 1/2. So taking the antiderivative of u to the 1/2, we're adding 1 to our exponent. So 1/2 plus 2/2 is 3/2. We're dividing by our new exponent. When I divide though by a fraction, I like to just think of it as we're multiplying by that reciprocal, which is 2/3. And then we have to add our c value. So we're almost done. We can simplify this a little bit, and we want to go back in, and wherever we see a u, we want to replace it with what we chose u to be in terms of x, 3 minus 2x. So notice those 2's cancel. We're left with negative 1/3. U here is 3 minus 2x, all raised to the 3/2 power plus c. Just because we had started with a radical, I would probably rewrite this as a radical. So negative 1/3, this is the same thing as the square root of 3 minus 2x quantity cubed plus c. Okay, so our next example, we have the integral of 1 all over square root of x times the quantity 1 minus square root of x. That quantity is squared, and then dx. So we don't know how to integrate this. I noticed that I would have a problem with that 1 over 1 minus square root of x quantity squared. If that piece was u, like 1 over u squared, I would be able to manipulate that. I could bring that up into the numerator and write it as u to the negative 2 power. So that's what I think I need to choose what u to be. And sometimes you don't know, you just need to try it. So we're hoping that if we choose u to be what's inside here, the parentheses, 1 minus the square root of x, or x to the 1/2 power. Differentiate both sides, so square root of u is du equals the square root of 1 minus x to the 1/2. So bring down our power, we get negative 1/2. Subtract 1 from our power, negative 1/2 dx. I'm going to rewrite this a little bit. So du equals negative 1 all over 2 x to the negative 1/2 power. Bringing that down, I can make it as a positive exponent, and that's really the square root of x dx. So if I get dx by itself, I can multiply by the reciprocal of what's in front of dx. So that would be negative 2 square roots of x du. So we want to go in, we want to rewrite what we had chosen u to be. So we have the square root, or integral of 1 over the square root of x, all times u quantity squared times dx, but dx is -2 square roots of x du. So notice I have a square root of x in the numerator and a square root of x in the denominator. So those are going to cancel with one another. So I have the integral of -2 all over u squared du, or -2 u to the -2nd power du. So add 1 to our exponent. Adding 1 to -2 gives me -1. Still have -2 out front. Divide by my new exponent of -1. I need to add my constant c. Negative is positive, so this is 2 all over u plus c. And when we write u, let's just write it in the same form we were given it originally, 1 minus the square root of x. That's okay. So this is 2 over the square root, or 2 all over u, which is 1 minus the square root of x, plus our c. Okay. So the next example is the integral of x to the 1/2 power all times sine of x to the 3/2 power plus 1 dx. We know how to take the integral of sine of x, but we don't know how to take the integral of sine of x to the 3/2 plus 1. And so we're hoping if we choose our u to be what we're taking the sine of, that's going to cancel with the x outside of it there. So if we let u equal x to the 3/2 plus 1. So differentiate both sides, we get du equals 3/2 x, subtract 1 from our power when we take the derivative. So 3/2 minus 2/2 is just 1/2 dx. So get dx by itself, we could multiply by 2/3. How about multiply both sides by 2 over 3 x to the 1/2. So we get dx equals 2 all over 3 x to the 1/2 power du. So go in and plug in what dx is and plug in what you had chosen u to be. So we have x to the 1/2 sine of u dx, but dx is the same thing as 2 du over 3 x to the 1/2. So notice that x to the 1/2 cancels, which we wanted. And now we have an integral with just u in there. We can think of this as 2/3 sine u du. So the antiderivative of sine u. So still have my 2/3 there. What can I take the derivative of to get back positive sine? That's going to be negative cosine of u. And then plus our constant c. So we have -2 over 3 cosine, but u was this x to the 3/2 plus 1. And then we have our constant c plus c. So next example, we have this integral of x times the square root of 4 minus x, and then dx. So again, we don't know how to integrate the square root of 4 minus x, but we know how to integrate the square root of u. So I would choose u to equal what's underneath the radical, or radicand, which is 4 minus x. If we differentiate both sides though, notice the x goes away. We get du equals derivative of 4 minus x is just negative 1 dx. So dx is the same thing as negative du. So when we go back in here and we substitute, we get x square root of u, and then times negative du. Or if we want to, this is negative x square root of u du. So notice how you have both x and u in there, and we can't have both of those variables in there. We want that integrand just to be in terms of u. So here's the trick. Go back and up here what we had chosen u to be, and let's solve for x. So we can get x by itself there, right? We could subtract 4 on both sides. We would get u minus 4 equals negative x. We can multiply everything through by negative 1. We would get x equals negative u plus 4. Or if we want to write it as 4 plus or 4 minus u is equal to. So now notice, let's rewrite that. We have negative x. The x is, we can rewrite as parentheses 4 minus u. Square root of u du. Well, we can manipulate this. This is the same thing as negative square root of u is u to the 1/2 power, right? All times 4 minus u du. So we don't know how to integrate that, but if we distribute that u to the 1/2 power to each term inside the parentheses, we would know how to integrate that. So negative u to the 1/2 times 4, so that's minus 4 u to the 1/2. Negative u to the 1/2 times negative u, so that's plus u, adding our exponents, 1/2 plus 2/2 is 3/2 du. So now it's in the form that we can take the antiderivative. So we have the negative 4 out front. We're adding 1 to our exponent of 1/2. So 1/2 plus 2/2 is 3/2. Divide by our new exponent of 3/2, or the same thing as multiplying by the reciprocal, which is 2/3. So that's just the first term, the antiderivative of u to the 3/2 power. So add 1 to our exponent of 3/2. 3/2 plus 2/2 is 5/2. Divide by 5/2 or multiply by the reciprocal of 5/2, which is 2/5 plus c. Okay, so just cleaning it up, negative 4 times 2/3, that's negative 8/3. This is the same thing as the square root of u cubed, but u is 4 minus x. So 4 minus x cubed plus 2/5 u to the 5/2. So the square root of u to the 5th, but u is 4 minus x. And that's raised to the 5th. We would have had a problem if we had chosen u to be our x value. We would have had more than one term underneath that radical, and we just wanted the one term underneath the radical to be able to take the antiderivative of that. The next example, we have the integral of the product. First parentheses is x plus 5 times the second parentheses x minus 5, and that x minus 5 is raised to the 1/3 power dx. So our problem again with this one is that x minus 5 to that 1/3 power. So again, let's choose u to be what's inside that parentheses, x minus 5. So taking the derivative of both sides, we get du equals just dx. But we're going to have the same problem like we did last time. We're still going to have x left in here because it's not going to cancel. So we have the integral of the quantity x plus 5 all times u to the 1/3 power times dx, but dx is the same thing as du, so times du. So again, we want to solve for, we want to rewrite x in terms of u. So we want this all to be in terms of u. So again, let's solve for x. X by itself, we would add 5 to both sides. We get x equals u plus 5. So the integral, parentheses, you see an x there, so let's replace it with u plus 5. But we still have that plus another plus 5 inside that parentheses, u to the 1/3 power du. So u plus 10 all times u to the 1/3 power du. So if we distribute that u to the 1/3 power, it will be in the form that we know how to integrate. So u to the 1/3 times u, add our exponents, that's u to the 4/3 plus 10u to the 1/3 du. So to integrate, we're just going to add 1 to our exponent. So u adding 1 to 4/3, 4/3 plus 3/3 is 7/3. Divide by c, 7/3 is the same thing as multiplying by the reciprocal, 3/7 plus 10. So add 1 to our exponent of 1/3. 1/3 plus 3/3 is 4/3. Divide by 4/3 or multiply by the reciprocal, 3/4. Indefinite integral, we always add c plus c. Nothing, I mean, it cleans up a little bit. That second term, notice 4 and 10 both have a 2 in common. So I can say 2 goes into 10 5 times, 2 goes into 4 twice. So we have 3/7. So u to the 7/3, that's like the cubed root of u, which we chose to be x minus 5. That's raised to the 7th plus 5, 5 times 3/2. That's going to be really plus 15/2. U to the 4/3, that's like the cubed root of u to the 4th. And u again was x minus 5 raised to the 4th power. Oops, and another plus c. Okay, so let's look at the integral of tangent of x. If we wanted to look at the integral of tangent of x, we can rewrite tangent of x. So let's look at the integral of tangent of x dx. But remember, tangent of x could be rewritten in terms of sine and cosine. Tangent of x is the same thing as sine of x, all over cosine of x dx. So we want to choose u to either be sine of x or cosine of x. And if you don't know, then just choose one and you'll see if it falls out or not. I can take the integral of sine of x. Okay. It'd be hard for me to take the integral of 1 over cosine of x. So let's choose u to be cosine of x. So the derivative of u is du equals derivative of cosine of x, that was negative sine of x dx. So if I solve for dx, divide by sine of x on both sides, I get dx equals du over negative sine of x. So this is the integral of sine x all over u times du all over negative sine of x. Which our sine of x cancels. And so we have the integral of negative 1 over u du. Okay, so this is where you have to remember what the antiderivative of 1 over u was. Remember the antiderivative of x to the n dx? That was x to the n plus 1 all over n plus 1. I guess I need my plus c. But n could not equal negative 1. Notice our n value would be negative 1. Recall if we had the integral of 1 over x dx, that was equal to the natural log of x, absolute value of x plus c. So the antiderivative of negative 1 over u is negative natural log of the absolute value of u plus c, or negative natural log of the absolute value of cosine of x plus c. Okay, so we have the integral of the natural log of the square root of x all over x dx. We do not know how to take the antiderivative of a natural log. I know that I could rewrite this a little bit, like this is the same thing as the natural log of x to the 1/2 power all over x dx. I can use my properties of logs and I can bring my exponent down front. So I could rewrite this as the integral of 1 or natural log of x all over 2x dx. Again, we don't know how to take the antiderivative of the natural log of x, but we know how to take the derivative of the natural log of x. So let's u be the natural log of x. So derivative of u is 1 du. Derivative of natural log of x, that was 1 over what you're taking the natural log of, which is x, times the derivative of what you're taking the natural log of, which is the 1 dx. So we can get dx by itself by multiplying both sides by x. So we get dx equals x times du. So we have the antiderivative or integral of the natural log of x, which is u, all over 2x times dx, which is x du. So notice our x's cancel, which we want. So we have really 1/2 u du. So now we can take the antiderivative of that. So 1/2, add 1 to our exponent of u, that gives me 2. Divide by my new exponent, which is 2 plus c. So we get u squared over 4 plus c. but u was the natural log of x. So we have the natural log of x quantity squared all over 4 plus c.